Okay, I am trying to answer a question that was posed by a student, and I'm having a little trouble navigating the screens. Okay, there it is. There's too many screens open, but let's see. There it is. Let me pull these up first. So this is what we're working on, and I'll click this one here. Okay, so with this image right here, we're looking at what is going on and why are some of these incorrect. So what I'm going to do here is, while I have this image up, I am going to add, let's see, I'm going to draw this image right here. I'm adding a page, then I'll draw the image. So add a page, hold on, right here. I need to view the image as I'm drawing it. So I'm going to have this up here, and I'll display my page when I'm done. So I'm trying to sketch, oops. Okay, the carbon, single bond, oxygen, H. So I'm going to draw it the best I can, and they want you to figure out what the hybridization is here. And then the double bond, oxygen, and this one's hybridization. There's another carbon back there. The nitrogen. Okay, that one's hybridization. Then this carbon. This is hybridization. Oh, oops. Okay. I think I got all of them. Okay, so essentially what I'm going to do here is I can now use my screen because I'm done drawing this. So with this structure right here in the background, what we have is the VSEPR model. So in the VSEPR model, they usually leave out the lone pair electrons. So they're usually missing lone pair electrons. What you're seeing here is not the complete picture. You may want to convert the VSEPR diagram or VSEPR model to the Lewis model. I tend to like to add lone pairs to my structure because of this issue right here. So what I'm going to do right now is, since I've drawn this picture right here on my iPad, I am going to bring in my lone pairs. So remember I mentioned this before a long time ago, that carbon, nitrogen, oxygen, and fluorine obey octet. Therefore, add lone pairs where needed. Okay, so you want to add lone pair where needed because you know that carbon, nitrogen, oxygen, and fluorine obey octet rule. So they all have to be surrounded by 8 electrons. So I'm going to start. The hydrogen is good, but the oxygen needs 2 sets of lone pairs. Okay, it already has 2 bonds. The 2 bonds make 2 electron groups. It's missing 2 electron groups, so just add lone pairs of electrons. Okay, that's what I'm going through, and I'm going to be doing that right now, adding lone pairs. Okay, this carbon right here is good. Wait, this carbon has too many groups. Oh, sorry, this last one is an arrow. Okay, so there's lone pair here, lone pair here. The carbon down here in the middle is good. The second carbon, third carbon is good. Nitrogen. So in this structure here, the oxygens and nitrogen are missing lone pairs. I'll put the lone pair here. So notice that the oxygen and nitrogen are missing lone pair electrons. Okay, so oxygen is missing 2, nitrogen is missing 3. Oxygen missing 2. Sorry, nitrogen is missing only 1. Nitrogen is missing one pair of electrons. Okay, so as you're working on your homework, that's pretty much it. Now that I'm done, I'm gonna go through and let me take a screenshot really quick. And so once I do that, because I'm gonna be sending this image right here to the person that emailed me. So hold on a second. I have to take a screenshot. This is not very easy to take a screenshot on my iPad while I'm trying to work on it. Oh no, I didn't get it right. Hold on. I struggle to take screenshots these days. Okay. I don't think I'm taking this right. Hold on, let me hold it vertically. That might help a little bit. Okay, everything I'm doing on my end is turning it off. Hold on. Give me just a moment. Okay. Anyway, I guess I'll just do it later. Sorry. Today is just one of those days. I don't know why it's so hard to do anything right now. But anyway, so having this, then I'll go through and count. I have 1, 2, 3, 4 groups here. So this is going to be sp3. Here I have 3 groups, 1, 2, 3. They're asking you to write in the hybridization. This would be sp2 because I have 3 groups, sp2. Around the carbon, the second carbon in the middle, I have 4 groups, 1, 2, 3, 4. So with 4 groups, I have sp3 hybridization. Around the third carbon, 1, 2, 3, 4. I also have 4 groups sp3 hybridization. And then the nitrogen, I have 1, 2, 3, 4, which is also sp3 hybridization. Okay, you have to make sure you count the electron groups. So remember, let me use a different color for these. These are just, they're not groups. These are just the arrow pointing towards the elements. That's not a group. That's not a group. And that's not a group. That was just the arrow pointing towards the element. Yeah, so this nitrogen here is surrounded by 4 groups, 1, 2, 3, 4. Okay. Okay, so hopefully that answers the questions. sp3, 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 and then only one sp2 because there's a double bond. When you have a double bond, you have sp2. Okay. So before I continue with the lecture, do you have any questions, maybe about the homework or something? If not, I'll continue from here. Okay, now that we're done with this, we'll move over to the issues with the valence bond theory. The valence bond theory was good because it was able to predict many properties better than the Lewis theory. Valence bond theory was able to give us bonding schemes, bond strength, bond length, and bond rigidity. We didn't get this information by looking at Lewis's theory of bonding, right? We're able to figure out with the bond strength. So the bonding scheme is the one where, remember, you have the bubbles around and it shows how the orbitals overlap. So this shows us overlapping orbitals. Bond strength shows that a sigma bond is stronger because of how it bonds. The whole head overlaps with the other head than pi. Okay. Bond length, we see that sigma is longer than pi because of how the orbitals overlap. Once again, this boils down to the way the orbitals overlap. The head-to-head overlap is the one that allows for this behavior, the difference between the sigma bond, the first bond, and the second bond. Bond rigidity, we see that when you have a pi bond, pi bonds are rigid. Okay, so we learned all these things from the valence bond theory. Sigma bonds are longer than pi bonds. Sigma bonds are stronger than pi bonds. We also learned while sigma bonds are flexible, pi bonds are rigid. Okay. However, there's still certain things that the valence bond theory is unable to do. However, there are still many properties of the molecule the valence bond theory isn't predicting perfectly. For example, we still have yet to explain why oxygen molecule has magnetic behavior. For us to see that, we're going to be looking at molecular orbital theory, and this will be our answer to the magnetic behavior of oxygen molecule. Okay. Not only that, second point, valence bond theory still presumes that electrons are localized in orbitals on the atoms in the molecule. It doesn't account for delocalization. Scientists were able to notice something called delocalization happened in elements, like we saw before. And this may be one of those homework questions that you want to go over. We saw this before, right? When we're drawing the Lewis structure. When you have a molecule like nitrate, where there are many valid Lewis structures, right? You have many resonance structures. We have 3 resonance structures like this, that you can actually draw 3 valid resonance structures from this nitrate molecule. That's the first one. I'm going to draw the second one, I guess below the first one. And you can see in the 3 valid Lewis structures, the part that's moving is a double bond. The single bond and the element remain exactly where they are. Okay, so from these, oops, I need more space up here. From these 3 Lewis structures that are all resonance structures of nitrate, what we end up with is a resonance hybrid. And the resonance hybrid reconciles or averages out these 3 Lewis structures, and we get the resonance hybrid. Remember, with the hybrid structure, scientists noticed that the bond order or the bond value between these 3 oxygens were about 1/3. Okay, that means that it appeared as though the pi electrons, the electrons in the second bond, these electrons right here, were delocalized between the 3 oxygens. So pi electrons, i.e., electrons from the second bonds, were delocalized. Delocalized is like shared or spread out. Delocalized between 3 elements. Okay, delocalized between the 3 elements. So if you were to figure out the bond value of this bond right here, you got 1.33 or 1/3, right? 1/3, like that, because the second bond was divided into 3 equal parts and then spread throughout between each nitrogen. Well, you only have 1 nitrogen and each of the available oxygens. Okay, so nitrogen and the available oxygen, and this happened 3 times. Since you only had 1 pi bond, that pi bond was divided into 3 and divided 3 parts, 3 equal parts, and then of course assigned to each oxygen. Anyway, so we have talked about scientists viewing that in the lab, but valence bond theory hasn't explained that, and Lewis's structure hasn't explained that. So we'll see this explained in molecular orbital theory. Okay, starting with electron delocalization. In molecular theory or molecular orbital theory, when we apply Schrodinger's wave equation to the molecule to calculate the set of molecular orbitals, what we see is, first of all, the solution to the equation has to be estimated. And the estimated solution is evaluated and adjusted until the energy of the orbital is minimized. So what we're doing here is we're making modifications to the solutions from Schrodinger's wave equation, okay, aka the orbital. And in doing so, in this treatment, the electrons end up belonging to the whole molecule, not just the elements or the atoms in the molecule. Okay? So as scientists were working on the Schrödinger wave equation, they realized that when they were assigning electrons just to individual atoms, when they were assigning pi electrons especially, the issue here wasn't the sigma electrons, the issue was the pi electrons. If an element, once again, like nitrogen had a double bond with an oxygen, but within the same compound, the nitrogen has a single bond with other oxygens. If you wrote the structure like this, the energy of the molecule was not very low. So in order to minimize the energy of the molecule from the orbital, they had to spread the electrons around, this double bond electron. In doing so, it minimized the energy. Okay? They were able to adjust and minimize the energy of the orbital. So in this treatment, electrons were now belonging to the whole molecule. So the orbitals belong to the whole molecule versus belonging just to that one element in the bond. This is called delocalization. And I told you here, remember the hybrid resonance structure. Okay. So we are going to treat molecules or orbitals in a molecule as molecular orbitals versus atomic orbitals. Okay. So from here on, molecules in an orbital are molecular orbitals. Okay, so it is our goal to take atomic orbitals that are just beginning to bond and form molecular orbitals out of it. So we're told here we're going to be using the method called LCAO, linear combination of atomic orbitals. The simplest guess starts with the atomic orbitals of the atoms. So this is elements before they bond. And then on the right side, we have elements in bond. And of course, we call these molecules. Okay. It starts with the orbitals of the elements adding together to make molecular orbitals. And this is called the linear combination of atomic orbitals method, kind of a weighted sum. So what we do here is if you take two atomic orbitals and you add them, you get two molecular orbitals. So let me do the math real quick down here. It's kind of, I'm calling it math, but I'm using that word loosely. It's just a weighted sum. Okay, so before I get into this, in valence bond theory, the previous section we just covered, we mentioned that two standard orbitals produce two hybrid orbitals. Okay? For example, if you have two standard orbitals like S and P adding together and they hybridize, they will produce sp and sp, two sp hybrid orbitals. In this section, we're saying, in this section, two standard orbitals produce, oh, not just standard, 2 standard atomic orbitals produce 2 molecular orbitals. Okay, so they're not hybridizing this time because this is a whole different section in the chapter. We have 2 molecular orbitals. And so we have to treat these molecular orbitals, the way they're coming together, as wave functions. So let me go back here and I'll come back to continue my statement. Because the orbitals are wave functions, the waves can combine 2 different ways. They can combine constructively. When they do that, the waves are in sync. And so there are times when we use the term sync to indicate getting along. You're telling somebody, oh my goodness, I feel like I jive with you or I sync with you. We are right here. We're getting along. So you have waves in sync where the highest parts, I'm forgetting words this morning. The highest parts are achieving the same point, or the lowest parts they're superimposable. That's the term I was looking for. The highest points are superimposable, the lowest points are superimposable. Or when you have destructive waves, you have the highest point opposite to the lowest point. So what I mean by that is, in showing the molecular orbitals, I'm going to show you how the waves look. These are waves that are in sync, or they're constructive waves. So constructive waves. Okay, so remember, the waves here we're referring to are the orbitals. Orbitals are technically waves. Okay, they have wave behavior. They have electron behavior. They have particle behavior. They have wave behavior. So the orbitals, we're focusing now on the wave behavior. When they're constructive, you have the highest points of the waves overlapping. So this is the part I was trying to illustrate, like that. They're in sync. Okay, I said in sync, and then I'm drawing hold on a second. Down, up, down, up, down. Okay, I tried. Where the highest points line up, the lowest points line up, the highest points line up, the lowest points line up. These 2 waves are constructive. So when you add these 2 waves, what you end up getting is a constructive wave, right? When you add these 2 waves, you get a wave with a bigger amplitude, like that, because they add to each other. Constructive addition. And then you have a scenario where you have a destructive wave. Addition. In the destructive wave addition, you have one wave opposite to the other wave. And so in this case, where you have the peak, you have the trough. So you can see how they're opposite to each other. They're completely out of sync. And so when you add these 2 out of sync waves, what you get is essentially this. They cancel each other out because they're kind of opposite to each other. It's like adding a positive to a negative, okay? So you have destructive wave addition and constructive wave addition, okay? So we're being told here, in this section, 2 standard atomic orbitals are added to produce 2 molecular orbitals. So when you're adding 2 atomic orbitals, they interact both constructively and destructively. When they interact constructively, they produce molecular bonding orbitals. So I'll draw a picture of this so that makes more sense. And this one here, molecular anti-bonding orbitals. Okay, so before we go into the lesson, we go deep into it, I'll talk about this from a way that maybe can make more sense to us. Okay, so imagine the 2 standard atomic orbitals are 2 individuals that want to engage in a relationship. Okay, so they're single at first and their goal is to get together. So when they're single and they haven't bonded yet, they're considered 2 standard atomic orbitals. In their intention to bond, they're going to form 2 molecular orbitals. Now, in this bonding theory, now they're explaining bonding. They're saying that the way the atomic orbitals interact is both constructive and destructive. So, the way I see this is like saying the way humans interact in a relationship, they have good ways of interacting that helps the relationship out when they are in sync with each other. These will all be categorized under the bonding orbital theory. Okay, the bonding orbital section. So these are the good behaviors, like maybe buying flowers, cooking for each other, being nice to each other. And then the same couple has bad behavior. I wouldn't even call it self-sabotaging, but relationship sabotaging behavior that they can't help but have because they're humans, right? There are good parts to them, there are bad parts to them. So when they have these destructive behaviors that work against the relationship, that is categorized under the anti-bonding orbitals. Because when I was a student, I found this section so boring, and I'm like, I can't relate to this. How can I relate real life to this? Not to say this is not real life, but you know what I'm saying, relatable life. And then later on, I was like, oh, destructive behavior, destructive tendencies. Yeah. So things that work against the relationship, right? And so at some point, we're going to actually match this against that. Not really match them, but the more bonding orbitals are filled, the more the relationship will survive and the bond will be maintained. And if you have more going on in the anti bonding part, the less the relationship will survive and the less the bond will be retained, and the more likely the bond will be very, very weak. Okay. So, counterproductive, destructive behavior is not good for the bond. Okay. Now let's go to the chemistry. So, bottom line, molecular orbitals. When the wave functions combine constructively, right, this is a good behavior, the resulting molecular orbitals has less energy. Remember we mentioned this earlier, less energy means more stable, more stability for the element, right? Less energy just means more preferred than the original atomic orbital. So what they're trying to say here is, once again, not trying to advocate for relationships, but to say that science shows that when these atoms combine in a good way, in a constructive way, the resulting combination is more stabilizing because it has less energy than even their original state. So when these atomic orbitals were single, they weren't as stable and as happy as they thought they were. Once they got in the bond, they have less energy, so they're more happy. Okay. This is called the bonding molecular orbital, and we're going to designate it as a sigma or pi, okay, depending on the kind of bond. Most of the electron density between the nuclei will be in the molecular orbital. These tend to have a lower energy and are therefore stabilizing for the molecule. The molecule prefers to have bonding molecular orbitals because it provides lower energy and is more stabilizing. When the wave functions combine destructively, self-sabotaging behavior, relationship sabotaging behavior, the resulting molecular orbitals has more energy. This is bad. Molecules prefer less energy, right? Have more energy than the original atomic orbital. So this is where you have toxic. I know I'm going into all these details, but I'm just saying that this is how I'm able to recall this, because I have a coworker who says, "I hate this section." I'm like, "Come to my side, try to relate it to the relationship," and she's like, "I don't want to do that. I just hate this section." I'm like, "Well, I used to hate it, and I started to understand it because I was like, wow, this is like psychology for the elements." Anyway, a lot of people hate this section. But anyway, so you have molecular orbitals interacting in a way where they're out of sync. For that reason, the interaction creates conflict within the molecule. How do we see that? We see more energy than even the original atomic orbitals. So this kind of interaction destabilizes the molecule. So molecules do not prefer this. This is called the anti-bonding molecular orbital, and to designate this part, we'll designate it as sigma star. I don't know if you can hear the sirens. If you can, I apologize for that. I don't know what's going on out there. And then pi star. So we will designate the anti-bonding molecular orbitals with a star. And we're showing here that when we draw the picture, most of the electron density when we're illustrating this will be outside the internuclear axis. And I'll show you where this applies. We'll have nodes between the nuclei. Once again, I'll show you in the picture. It'll make more sense. Nodes are areas where you have no none of the electron cloud. Where you have, like, if you have a case like this, the p orbital, the center of the p orbital, the middle of the p orbital, is considered a node because you don't have any electron density there. Okay. We're told when we have molecular orbitals or antibonding molecular orbitals, we have higher energy in the molecule, and this reduces the stability of the molecule. Okay, so we're now seeing how the interaction in the 1s orbital takes place. So here are, once again, this is the before, this is the after. So these two 1s orbitals want to bond, right? So they bond two different ways. The top one is destructive, the bottom one is constructive. So please notice in this picture here, they put the destructive one first, not because that happened before the other one. They're happening at the same time, but what's happening is they have lined these up according to increasing energy level. So remember, the anti-bonding molecular orbital is at a higher energy than the original orbitals. So it is fair for me to draw the original orbitals right here. The original 1s orbitals where the energy level was between the higher energy anti-bonding molecular orbital and the lower energy bonding molecular orbital, okay? So once they bonded, you can see the bonding molecular orbital got even lower. Once they anti-bonded, the anti-bonding molecular orbital got even higher, right? So this is showing you how they destructively interfere with each other or constructively interfere with each other. That's when they're interacting, getting together. And so you can see here, right? You see how between the two nuclei, because they're not interacting constructively, we end up with a node. A node is a region where around the nucleus where we have no electron density. The bubble doesn't go in that area where node is. Okay, it's like node is nada, nothing, nothing there. No electron density, no bubble. Okay. So we have the anti-bonding molecular orbital, bonding molecular orbital. In the bonding molecular orbital, it appears to me like these two orbitals just merge with each other, right? They just spread around. So this is bonding, this is anti-bonding. You want to be aware of this because I'll just say, at least we are introducing this in 1412, oh sorry, 1411, but in organic chemistry, you have to know how to draw this yourself and be able to label each one and explain what's going on. Okay. So we've seen this here. I talked about all this before. Electrons in bonding molecular orbitals are stabilizing, lowering the energy, and they're lower in energy than atomic orbitals. Electrons in the anti-bonding molecular orbitals are destabilizing. They are higher in energy than the atomic orbitals. They are located outside the internucleus axis. If you drew an axis here between the nuclei, you can see how there is no electrons. If you drew it vertically, there's no electrons here, right? And what else? Electrons in anti-bonding orbitals can cancel stability gained by electrons in bonding electrons. So electrons in anti-bonding orbitals cancel stability. So this is what I was saying earlier, that this would be like relationship sabotaging behavior that cancels out the good that was done in the relationship. Okay. So let's go ahead and see this. There's one more thing I want to cover before I start drawing the orbital diagram, which is when we work on this, we'll be figuring out bond order. Remember earlier I told you about the bond order between the hybridized version of nitrate molecule, which is also, sorry, nitrate ion, which would be N single, N single, N single with the O here, O here, O here. Then you had a third of a bond, a third of a bond, a third of a bond. I told you the bond order here, bond order was 1 1/3, we will be figuring out bond orders for the molecules that we're drawing or we're looking at. What is the bond order? How do we figure it out? We're told bond order is 1/2 of the difference between the number of electrons in bonding and anti-bonding orbitals. Here's the formula. Bond order is 1/2 bonding electrons minus anti-bonding electrons. So you can see right here, the anti-bonding electrons take away from the bonding electrons, right? So if you have equal number of anti-bonding electrons as you do bonding electrons, essentially no bond will form, okay? Because they take away from the relationship. Okay. So in this process here, we're told only need to consider valence electrons. Only use valence electrons when you're drawing your molecular orbital diagram. The bonding order or the bond order may be a fraction. Okay, once we get our bond order, what does it mean? If we get a higher bond order, that just means the two elements are bonding with a stronger bond and the bond is shorter. If the bond order is 0, if we figure it out and the bond order is 0, then the bond is unstable compared to the individual atoms and no bond will form. If the bond is very unstable because the anti-bonding electrons, we have too many of those compared to the bonding electrons, or even if we have equal number, then the bond will not form. A substance with paramagnetic behavior, when you draw its molecular orbital diagram, will have unpaired electrons, okay? So remember, in this section, we'll finally answer what's going on with oxygen molecule. If all electrons are paired, it will be diamagnetic. So I've already talked about this bond order. Make sure you write this down. Bond order, half bonding electrons minus anti-bonding electrons. Okay, finally the diagram. We're right here. Let me draw my own, and then we'll go from here. We're looking at bonding. So I'm going to illustrate this real quick. I'll draw my own down here. This is atomic orbitals. So these are the atomic orbitals before they form a compound or a molecule, right? Atomic orbitals. So we're drawing the orbital diagram. Since we're going to be using 2 atomic orbitals, by the way, we're drawing the molecular orbital diagram from H2. H2 is hydrogen molecule, right? Remember, H2 bonds like this. In the lowest structure, you have 2 hydrogens like that. As simple as that. We're going to draw this according to molecular orbital theory. I call that MOT in short. And then when the molecular orbitals get together, we're going to have 2. One up and one on the bottom. Okay, so let's go back. Since this is an orbital diagram, atomic orbital, I have to get the configuration. So let's go back to hydrogen. Hydrogen just has 1 electron, right? So its configuration is 1s1, correct? So in the 1s sublevel, I'm going to place 1 electron, up, up. Since I'm taking 2 atomic orbitals, 1 from each hydrogen, and combining them linearly to make the molecular orbitals, 2 atomic orbitals will combine to make 2 molecular orbitals. I already said that earlier, right? One of the molecular orbitals will be designated bonding. The lower one is bonding because it has lower energy. Bonding molecular orbital. The top one will be anti-bonding molecular orbital, okay? Since hydrogen is in the s orbital, the bonding one will be labeled sigma, and the anti-bonding one will be labeled sigma star. I'm trying to think of everything. Okay, once these combine, they usually kind of join them here with these lines here. Once these combine, now you take the electrons from either side, 1 electron from the right, 1 electron from the left, combine them, and you place them in the orbital. You have to use Hund's rule, Pauli's rules, all those rules, right? And Aufbau's rule. Fill the lower molecular orbital first before you go to the next one. So the lower one can handle 2 electrons. So I place the 2 electrons here together like that. And I'm out of electrons because I had one from the right, one from the left. Then I have to figure out my bonding order. My diagram is done. My bond order for hydrogen is 1/2 bonding electrons minus anti-bonding electrons. Okay, 1/2. Bonding electrons, I have 2. Anti-bonding electrons, I have 0. Right? You see, I placed nothing in the anti-bonding section. So I have 1/2 times 2, which is 1. So we did all this just to say when 2 hydrogen atoms bond, they form a single stable bond. Oh, from here we also learn sigma bond, right? That's it. I did all this just to say that. Technically, I could have said that from Lewis's theory, right? But we are learning an account from 3 different major groups. Lewis groups, valence bond theory group, and then now molecular orbital theory. Okay? Hold on a second. I thought I saw something. Oh, I heard something. Oh, from the valence bond theory, s orbitals, because remember each hydrogen electron is in the s orbital, right? Do I saw my periodic table somewhere here in the back. Yeah, I'm about to pull the mess I have in the back over here. There it is. Yeah. Hold on. Can I make this bigger? Because the hydrogen is in that 1s sublevel, it uses the s orbital to bond. So because of that, it has to do sigma bonding. And so with that, let me see if I can pull this up. Yeah, s orbitals are round, right? The 1s is this smaller but round. When these overlap, they overlap head to head because they're round. No matter how they overlap, it's always head to head. And so head to head overlap is considered sigma bonding. With the p bonding, or the p sublevel, let me see. Yeah. So with the elements, as far as bonding is concerned, with the more complex sections, we focus more on the S and the P. Even though we did do the D with the valence bond theory, but the variation is seen more with the S orbital and the P. So what I'll say is this: S orbitals always do sigma bond. So S orbitals always participate in sigma bond. And so we learned this in the valence bond theory section. They can't do anything else because their shape is round either way. No matter how you approach the s orbital, you will end up with a head-to-head overlap, whether it come from here or from here or from here. But when it comes to the p orbitals, that's when we see the 2 different ones. So the section what I'm explaining right now was covered in the valence bond theory section, the section before this section here. With the p orbitals, because the p orbital, the way they are lined up, I'll start with the px. Px is lying down horizontally, right? If 2 px orbitals approach each other, they will do a head-to-head overlap because it's like they're trying to interact while they're both lying down. It would be like 2 people wrestling or something, and they're holding each other head to head. They're somehow interacting with their heads like that. So it's literally called a head to head overlap. But this one here is still sigma bonding because the fleshier part of the orbital is interacting, right? And then you have, and these are 2 px orbitals. Okay, so px and px. So if you look at the axis they're on, is on the x-axis. Ooh, bad picture, but you get the idea. And then when you have two py orbitals interacting, the py orbitals, because they are oriented vertically like that to each other, they can't interact in the head-to-head fashion the way the px orbitals are, because of how they are relative to each other. To me, these two orbitals are standing next to each other. So the way they can interact is side by side, because neither can lie down. If they lie down, they stop being px and they become py. So we're trying to see how py's interact. When two py's interact, the only way they can interact and maintain their orientation is side by side. So the head will interact side by side like this, and then the bottom here. So this is called side by side interaction, and this is called the pi orbital. So as far as what we have studied right now, pi interactions, but yeah, the sigma pi bond and pi orbital pi interactions. The sigma interaction can happen in P, but we see it in Px. The Py and Pz both do pi bonding. Okay, so the second one, right. So when we get to the p orbital, we'll do the sigma first to take care of px, because when the bonding happens, it happens in the order of px bonding first, then py, then pz. So we know px does sigma bonds. Then py will do pi bond, and then pz will do pi bond. So essentially in the last chapter, let me go to the triple bond where we saw px, p, whatever. No, it's not the last chapter, sorry, the last section. Not that one. That one. Let me talk about triple bond first. Where we had the triple bond. That's still a double bond. Where's the triple bond? I got a lot of pictures here. In the image, because I don't know if that's in your homework. I know some of these questions are in your homework. Man, okay, hold on. Let me scroll from the side. It might go faster that way. There it is. Yeah. In this image here, of course, you see the head-to-head overlap here, right? In the middle, that's going to be and then P, the first one was already used. So this is going to be a pi over, let me use a black marker. Pi overlap, and then down here we have also another pi over. Two pi overlap based on how they're overlapping. And the pi overlapping looks, it happens after the sigma. The sigma occurs first, then the pi comes in later, because the pi is always bridging over the sigma bond, which explains how they bond. Okay, they're always trying to, like a shell or a bridge, bridging over the sigma bond. So it's kind of like this happens first, and the second one has to bridge over the first, like that. And it bridges on top and bridges on the bottom. So the pi bond looks something like that. Pi bond, and then the sigma bond was the first one. Okay. Anyway, since we've seen all that before, we're seeing a very different version of the same story. This time is a story as told by molecular orbital theory group, right? Okay, so we've seen that. Now we're going to be seeing how, okay, you're welcome. We're now going to be seeing how we can predict bonding. So not only are we seeing bonding, we saw the hydrogen, we're now going to predict bonding in He. So we've said before, theoretically, group 8 elements don't really bond very well with other elements. They don't even bond with each other. They're inert. They're practically inert, meaning they don't like to bond. Okay, so instead of trying to waste your time in the lab trying to get these to bond, how can you theoretically see they're not going to bond? How can we predict the kind of bonding behavior we will see in elements before we go to the lab? Because scientists like doing that. They try to predict the outcome. They go to a lab to prove it. That makes science and what you're doing in the lab more exciting, because you're doing an experiment, yes, but you're trying to prove yourself correct. Okay, so we're going to be looking at He2, and we'll see in the end why there is no bond between these two. Okay, so does He2 exist? Okay, we'll see. We have a helium, we have a helium. These are about to bond. So remember, the way we write this is outside in. You write your atomic orbitals on the outside first. This is a whole different section from the other one, right? Molecular orbital on the inside. So helium, I don't know if I have that other table here. I know it's somewhere in the back. Helium is here, right next to hydrogen, right? And so helium is still bonding with the 1s orbital, so we're going to be filling the 1s orbital, but because helium has 2 electrons, both electrons are in the 1s orbital. Okay? What did I do? Okay, I'm trying to just minimize this. Bring this back up. Okay, so I just need one block and one block for the 1s orbital. And then when these join to form the molecular orbital, we'll get one block, one block. Anti-bonding, bonding. Since they're S, guess what? Sigma, sigma star. Okay. Oh, how many electrons? Each helium has 2 electrons, 2 electrons, 2 electrons. Put up and down, up and down. Okay. Once we mix them, now we're trying to place 4 electrons total, right? 2 from the right, 2 from the left. Up, down, that's full. Up, down, now that's full. I've placed all 4 electrons from the atomic orbital section into the center molecular orbital section. Now I have to figure out my bonding order. My bonding order is 1/2 bonding electrons minus anti-bonding electrons. Okay, 1/2 bonding electrons. I had 2, right? These 2 right here. I'm referring to these 2. And then anti-bonding electrons, I also have 2. So while helium made an effort in this quote-unquote relationship, it also did a lot to sabotage the relationship. As much good as bad. And so in the end, it kind of canceled out, right? We have 1/2 times 0, we have 0. Bond order is 0. In other words, bond will not form. Okay, sorry. The other helium is like, you know what? You tried, but you also did a lot of bad things. This relationship is not going to happen. Bond will not form. The bond order is 0. Okay, after we've seen that He2 does not exist, how does He2 plus exist then? Let's see. So in an effort to try to see to make 2 heliums bond, scientists decided to bond He2 plus. And this actually exists. So how do we prove it exists? Same thing like what we did before. Remember in chemistry, plus means lost 1 electron. Okay, so I have a helium here. I have a helium again. From here, I'll get my atomic orbital. I'll get my atomic orbital. When I combine them in the center, I'll get molecular orbital. Okay, so helium being in the s block has 1s, 1s. Each helium will combine to form 2 molecular orbitals. Top one, anti-bonding. Bottom one, yeah, I'm beginning to get inconsistent. Bonding. Bottom one, sigma. Top one, sigma star. Okay. Okay, so they said it's He. I have 2 He's. Then make the left one 2 electrons up and down. One of them has to lose electron, right? So this one here will be He plus, and I only have 1 electron because this one would have lost 1 electron. Okay, so it's only left with 1 electron. Now they're about to form a bond. So when they form a bond in the center, in the molecular orbital section, we only have 3 electrons to work with. So I put up and down 2 electrons, up, third electron. Then I have to do my bonding order. BO equal 1/2 bonding electrons minus anti-bonding electrons. Let's see. 1/2. 2 minus 1. 1/2. 1. 1/2. Okay, so the bond between helium and helium after it's lost an electron, it's not going to be a strong bond, but you can make a weak bond. So we draw, if it's not a full bond, we draw it with a dotted line because this is a half bond, right? A half bond order. So we draw with a dotted line. This bond will exist and this molecule will exist. It just won't be as strong as the one with the full bond, okay? So this is the bond right here, essentially between the two H's, or the HE, right? It is a weak bond, but the bond does exist. So what do they say here? Yeah, half bond order, okay? Okay, now that we've seen all that, summarizing molecular theory, molecular orbitals are linear combinations of atomic orbitals. Total number of molecular orbitals formed must equal the number of atomic orbitals in the set. I won't go over this again. I've already mentioned it. The way they combine, lower energy. I've talked about all that stuff. So what I'm going to do right now is see. Let me see this example, practice problem. I want to get to the ones that have p orbitals. Okay, I guess we're close to that. I'll do one more, then we'll get to the p orbitals part. So in this one here, actually, I'll just explain this. We are showing the bond order on H to negative. Remember, in chemistry, negative means extra electron. Okay, you have an extra electron that was not there originally. Okay, so we need two hydrogens, the hydrogen to the left, the hydrogen to the right. Oh, this shows you the energy is increasing from lower to bottom. So this is low energy, and this is high energy. Okay, so we have our atomic orbitals right here. Atomic orbitals, atomic orbitals. They show you the configuration for the hydrogen. So I usually write one of these hydrogen has an extra electron. This one here. This hydrogen on the right has 2 electrons. The one on the left has 1. Okay, so we have H minus. Okay, so since the one on the right has an extra electron and hydrogen normally has 1 electron, you take 2, you add 1, we now have 3 electrons to work with. So of course, in your molecular orbital portion, you have your bonding. They don't write the word bonding because the lack of star implies it's bonding. The star here is anti-bonding. But you can see 2 electrons, 1 electrons. Our bond order is going to be 1/2, 2 minus 1. So it's going to be 1/2 in the end, right? Yeah, so you have a weaker bond than you have in the regular hydrogen molecule, but the bond does exist. It is weaker, but it's present, right? Okay, I won't do this extra practice problem. We're told it is weaker than the regular one. Remember the regular H bond was a single bond, so it's a single dotted line. So this is stronger. The one we saw right now, H dot dot H, because it's half a bond, not a full bond. This is going to be weaker. So H2 minus is weaker than H2. There's a minus missing somewhere in there. Okay. Now we're looking at elements in the second period. In the second period, you want to focus on the valence electrons again. So even though lithium, we're looking at lithium molecule here, right? Each lithium technically has 3 electrons. So the sublevels we use for lithium are both the first and the second one. Let me see if I can find this in the back. Can I pull this up somewhere? Okay, there. Okay, so lithium uses both 1s and 2s, and lithium has 3 electrons. So we need both 1s and 2s. But in drawing this part here, we don't even need to draw both of them. We just show the valence, right? So even though lithium technically has 1s2, 2s1, we are going to show the valence only because this here, the 1s level kind of cancels out. So you can see they're showing you just the 2s level where the 1 electron is. This part here is not shown. Okay. So the 2s level for the lithium, same thing. You have one lithium atom on the left, one on the right. Sorry, right, left. Ha. And then when you make the molecule atomic orbitals, or they label them right here, molecular orbitals, the 2 go in the bonding, there's 9 in the anti-bonding. The bond order here is going to be 1/2, 2 minus 0. We end up with a bond order of 1. When 2 lithium molecules combine, we have Li, Li, like that, Li, Li. Okay? Beryllium molecule, same thing. Beryllium molecule, each beryllium has a configuration of 1s2, 2s2. This inner sublevel is not shown because it's not the valence sublevel. Okay? You want the outermost energy level. This one here is the one that's shown. So you can see this is a 2s sublevel. Below the 2s, we have the 1s sublevel. That part is not shown. Okay. Over here, there's 2 electrons on either side, 2 electrons here, 2 electrons here. When you combine them in the middle, you have 2 here, 2 here. We end up with bond order of 1/2, 2 minus 2, which is a bond order of 0. Okay? So now we are looking at interacting p orbitals. We saw how the s orbitals interacted. Now we're looking at the p orbitals. You see how they start with a px first? They start with a px. So this is 2 px orbitals interacting. Now this is the version of the molecular orbital theory versus what we saw in valence bond theory. When px's overlap, or I shouldn't use the term overlap. Ooh, bad. This section, the term is combine. Overlapping is in the other section. When the 2 p orbitals combine constructively in a good way, they create the bonding orbital that looks like this. I don't know, this reminds me of a candy. You know, candy, the circular candy in a wrapper, and this is the wrapper right here. But you see, the 2 parts that are agreeing with each other, right, in sync with each other, they just reinforce each other, and now you have a huge, big region here. And this is 2p s. Wait, what is this s? It's supposed to be 2p sigma. Are you kidding me? They put sorry. This is supposed to be sigma. I don't know what this s is. It's supposed to be sigma. And then sigma antibonding. Remember, px, the way this is overlapping here, is sigma. And then here, the way these overlap is sigma antibonding. So 2p again, sigma antibond. And they show you how they're interacting the antibond by showing you different colors. They are out of sync, and so they're out of sync, so they don't even interact at all. And then most of the electron density is away from the bond. So here it's kind of like collaborative behavior. The relationship works. This is anti-behavior towards the relationship. Selfish tendencies, right? Where most of the electron density, the step that's required to make the relationship work, is taken away from the relationship. So you have anti-bonding, and this area is now a node. Okay? Okay. Let's see what's happening in the PZ and PY. PZ, these orbitals are vertical to each other, or I should say like side by side, right? So when they interact, the blue region overlaps to give you this part here. The red region overlap right here. We actually end up with a node here, but it's no big deal. Here, we end up with anti-bonding. Once again, it's almost like they repel each other, right? Because of the way they're oriented, they're out of sync with each other. So here we see the pi interaction. This is pi bonding, and then pi anti-bonding. Okay, and this is a PZ, this is a PY. PY, same thing that we're seeing here, just lying differently. Okay. Okay, so I wanted to finish this chapter, so I'm going to go through a little faster. With this part here, I would suggest to you, you can try to memorize this. If you're taking like a state exam or something, the way you guys are taking your exam here, you can just copy it. The structure we have here, or the organization or the order of the orbitals we have here for the atomic orbitals and molecular orbitals, works for boron, carbon, nitrogen on the left. On the right, it works for oxygen, fluorine, neon. So just in case you're wondering what the order is, I'm going to pull up the periodic table I have down here. That's not it. Not that. Oh, is it down here? Okay. In the P block, the first three elements, boron, carbon, nitrogen, they use the same bonding orbital structure to bond. Oxygen, fluorine, neon uses the same, right? So oxygen, fluorine, neon, O2, F2, Ne2. And the first one was what? B2, C2, N2, okay? Now that we understand how this relates to the periodic table, if you ask any questions about these, you have to use this. So I'm gonna show you guys the bonding for N2. Okay, let me go through this real quick. N2, nitrogen is right here. I'm gonna combine these two. Nitrogen has 7 electrons. So nitrogen essentially is 1s2, 2s2, right? The first two are 1s2, 2s2, 2p3. While I'm here, I'm going to work that for oxygen too. Oxygen is 1s2, 2s2, 2p4. So I'm going to go back to my right here and work this out on here. So remember, we are only working with the valence electrons. So I don't really need this. I'm just going to use these two because down here, you see what level we're on? 2s, 2s. Nobody's showing the 1s level. So I know each nitrogen has 2 electrons in the 2s level. So I have my nitrogen on the left with 2 electrons here. My nitrogen on the right with 2 electrons here, right? Because it says so, 2 electrons. And then each nitrogen has 3 electrons in the 2p level. 3 electrons, 3 electrons. They don't write that, but I liked writing it that way because it helped me tie in configurations to this chapter. And it helped me know what I was doing, right? So 2s2, 2s2, 2p3, 2p3. Okay, so in here, I have up, down, 2 electrons, right? Up, down. So in the middle, I have 4 to place. Up, down, up, down. Okay, moving on up. Oh, by the way, let's examine what we have here. In the 2p sublevel, we have 1, 2, 3, right? Orbitals. 1, 2, 3 orbitals. So we have a total of 6 orbitals. The 6 are distributed this way. 2 here, third, fourth, fifth, sixth. 2 are pi. This is probably py, pz. And then the sigma one is px. Remember, px's do sigma bonds. And then py, pz. Okay? But what you want to recognize is the first two are pi. One is sigma because experimentally it has lower energy. The third one is pi star. And then the fourth one is sigma star. Okay. So here I have to place what? Right? Up, 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 up. When I get to the middle, I mix up the 3 and I get 6 electrons. So 2, 3, 4, 6. When I place my 6 electrons in the middle, the molecular orbital, that's what I get. Now I have to figure out the bonding order for nitrogen. For N2, my bond order is, can I write this in shorthand? I'm writing too big, like I have a lot of space. My bond order for N2 is BO equal 1/2 I'm going to highlight all my bonding electrons. This is bonding, these are bonding, and these down here are bonding. You don't have, but I like to include them. I feel all of them. I have minus the 2 electrons, these top ones here, right? So 8 minus 2 is 6. So 1/2 times 6 equals 3. Wait, don't we already know that when 2 nitrogens bond, they bond with 3? Yes. Able to see when they bond, one of the bonds is a sigma bond. So nitrogen forms a bond, 3 bonds with another nitrogen. Okay? And so this bond here is sigma, then the other 2 are pi. Pi, pi. Okay? Oh, by the way, if they ask you, nitrogen is diamagnetic. How do I know that? If you look at all the orbitals that have electrons in them, you only look at orbitals, not the atomic orbitals, because we're looking at the bond, the orbitals in, right? All of these are paired. Every electron has or orbital mate. Now, I'm going to answer the question about oxygen. Once again, if you look at this structure here, I heard something. Oh, no. Sorry, I don't know if it's my internet or if it's just this. It bumped me out. Okay. Where was I? I was here, right? I don't think I needed the other one. We're about to work on oxygen. So as you can see right here, they don't have the 1s sublevel, so I can leave this out. All I need is 2s and 2p. So for each oxygen, for 2s, we have 2 electrons here, 2 electrons. For each oxygen 2p, I have 4 electrons here, 4 electrons here. I can now erase this because I don't need that anymore. But we are working on with 2 oxygens, right? Okay. So, oops, 2 electrons, 2 electrons. That means up, down, up, down. In the molecular orbital section, this is going to be up, down, up, down. Okay. Now, you can choose to include the 2s when you're figuring out the bonding order part. Some people leave it out because the number of electrons here matches the number of electrons here, so they kind of cancel each other out. It's okay to do either. Okay. Okay. Oh, here, 4. Up, 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 3, 4, right? Up, 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 3, 4. Okay. So we have 8 electrons to place in the middle. 1, 2, 3, 4, 5, 6, 7, 8. Uh-oh, we have unpaired electrons, okay, in the oxygen molecule, O2. Okay, so when I'm writing or figuring out the bond order, this time I'm going to just stick with the top part. I'm just going to use the top part here because I know the bottom part kind of evens out or cancels out. So I'm going to stick with the top part just to show you different ways of working this out. 1/2, 6, right? These are all bonding down here. Minus 2 is 1/2 times 4, which is 2. So we know when 2 oxygens form a bond with each other, it's double bond. We have a lone pair here, but it's double bond. We get that. Okay, got that. But what about this part right here? We finally see the unpaired electrons. So the unpaired electrons result in a paramagnetic. If I can spell, paramagnetic behavior. So let's take a moment and think about it. Oxygen gas condensed to a liquid state. Oxygen is a nonmetal. Are we saying what we're saying? Yes, we are. In the molecular form of oxygen, remember we're only judging the central part. That's the molecular orbital, right? This is part here. When the oxygen molecule is formed, even though oxygen element is a nonmetal and the oxygen molecule is still a nonmetal, because the oxygen molecule has unpaired electrons, it behaves like a metal. Yeah. Scientists were shocked to find this out. Like, what? I gotta tell somebody this. I gotta call my mama. I gotta call somebody and tell them this discovery. You have a nonmetal in the molecular form behaving like a metal. It was very unexpected, right? Why? Because, and then if you ask Lewis, like, I don't know, valence bond theory. Well, let's see. Overlap, overlap. I still can't see it. Molecular orbital theory then steps in and explains how this is happening and then shows the evidence, right? So as a student, I'm not gonna lie, I didn't, because the teacher didn't dramatize it. I like a little bit of drama in my science, right? I like a little conflict, a little drama. They didn't really explain why it was so important and the molecular orbital theory was able to show a behavior that the others couldn't. They just said in a monotone voice, the unpaired electron shows existence of paramagnetic behavior. I'm like, uh-huh, mm-hmm, yeah. I didn't even realize then that oxygen was a molecular compound, a nonmetal. I only realized this as a teacher because I'm explaining. I'm like, wait a minute, this is a molecular compound. We're talking covalent bonds here. Metallic behavior, what? Yeah. So it's very exciting. Very, very exciting. Once again, we're judging paramagnetic behavior at the molecular level, not the atomic level, okay? So only when the molecule is formed. So we can see right here. Oh, what do they have? Oh, they have the bond order here. They have the energy required to break the bond. So bottom line here, we see uh, greater number of bonds, comma, greater energy to break them. The more bonds you have, the more energy you have to apply to break them. Okay? Bond order, where am I? Yeah, so if you look at this and you do the math and do the bond order, bonding electrons minus anti-bonding, you get a bond order of 1, 2, 3. So you can see here, boron, if two borons bond with each other, they will form a single bond according to molecular orbital theory. Now, molecular orbital theory, as it says, is theoretical. Just because you can write it on paper, then the goal of the scientist is, if I can put it on paper, can I prove it in the lab, right? Can I go to the lab and replicate what I have on paper? Is it possible? Of course, once you can do it, you have bragging rights. So two bonds will bond with a single bond. Two carbons, if this is possible, will bond with a double bond. Two nitrogens will bond with a triple bond. Okay, you have lone pair here. I guess you have two sets of lone pairs here. Okay, and then you got boron. It's complicated. And then with oxygens, two oxygens will bond with a double bond. Fluorine, single bond. Neon, no bond. Right? They don't like to bond with each other. Okay, what about behavior? This is going to be paramagnetic because you have two unpaired electrons. This is going to be diamagnetic. No unpaired electrons. Diamagnetic with nitrogen. No unpaired electrons. Oxygen, also paramagnetic because we have two unpaired electrons. Fluorine, diamagnetic, no unpaired electrons. Neon, first of all, the compound is not forming, so why are we even judging it? I don't know. I didn't want neon to feel left out. Okay, but based on theory alone, diamagnetic. Okay, no unpaired electron, diamagnetic. Partially filled orbitals or the unpaired electron present, paramagnetic. Okay. I like the term partially filled orbital because paramagnetic, partially filled, par. That's how I learned this when I was in middle school. We didn't get this far in middle school. We got this far in high school, but we're learning about partially filled orbitals in middle school. And I'm looking at the teacher like, what in the world? Why did I sign up for this class? Why people? Now I'm like loving it because I finally get it, right? It's so different when you finally get it. Okay, with this one here, just like we did before, the adding it, the extra electron, I want to make sure that I'm not skipping anything important as we're going over this. Oh, okay, we're close to the end, so I'll make it. We're close to the end. With this one here, let's see. Oh, okay. So here we have the two nitrogens, 2s level, 2s2, 2s2. Now they said N2 minus. So one N is, let's see, nitrogen. I'm going to use this one here. Nitrogen. I'm just using the 2s2, 2p3. Oh, okay. 2s2, 2p3. And then N minus would be 2s2, 2p4. Okay. I was needing a little bit of hand holding. That's why I have my resources. There are times when I'm like, my brain is kind of stuck. I need some hand holding. I need some help. Right. So let me make the nitrogen on the right, the one that has the extra charge. So this N minus, N minus. When we get to the 2p level, this will be the one that has the extra electron. So it'll be 2p4. This would be the regular N, regular N. Once again, you don't have to do these additional things. I like them because they keep me grounded. I mean, these are my notes. So I tend to not write less. No, I do the most, like I've been told. Because it helps me out. I know how I am. I know how I second guess myself and I question myself. So I'm a critic. So I need to make sure I write enough so that when I'm looking at this tomorrow, I'm not asking myself all these 1 million questions. Okay. 2s2, up, down, up, down. The 2s2 forms these two right here, right? Bonding, anti-bonding. So up, down, that takes care of that. 2p4, up, down. That's 4. Up, that's 3. These form these, and they form those. Okay. Now we have to place 3 and 4. 7 electrons, up, down. That's 4, 5, 6, 7. Ooh, this is paramagnetic, right? 1, 2, 3, 4, 5, 6, 7. Okay. Isn't that what they have here? Yeah, that's what they have here. And then bond order. This is a lot neater. Bond order, 1/2. I'll use the top ones only. Bonding electrons, what are these? 6 minus 1. 1/2 times 5. 2/2. If it's 2/2, you have a situation here where when the nitrogen forms a bond with another nitrogen and it's negative like this, 2 bonds are solid, and then the third one is going to be a half like that, 2.5. Okay. I mean, you most likely won't, at this level, you most likely won't be asked to draw anything this complex, but I'm just showing, since we came this far, I'm showing you how it will look. Okay. So we already went through all of these. I did the oxygen one and the nitrogen one, so you got to see how this worked out. So finally, I wrapped this up with this because we still hadn't talked about delocalization. So here they show us ozone. When atoms are combined together, the atomic orbitals of all the atoms are combined to make a set of molecular orbitals. In other words, from Lewis's structure, what we're seeing is the double bond is forced between a specific, is localized. It stays between a specific element in the compound or two specific elements in the compound. If we were to label this oxygen 1, 2, and 3, we can say for the left resonance structure, right? That's what these are called. Let's call this resonance A, and this is resonance B. For the left resonance structure, resonance A, the double bond is between oxygen 2 and 3. For the right resonance structure, resonance B, the oxygen is between oxygen 1, the double bond is between oxygen 1 and 2. You see? It's obvious. So that's your argument. Imagine you're in the court of science and you're arguing. These are two different structures. Why? On the left structure, the oxygen exists between, the double bond. Oh my goodness, my brain. The double bond exists between oxygen 2 and 3. For the right one, the double bond exists between oxygen 1 and 2. By virtue of that, these are two different molecules. And the scientists tag the oxygen with radio traces so they can tell which oxygen it is. So you can't just say, well, it looks flipped to me. No, they tag them so they can know this is for real two different molecules. Now, molecular orbital theory says you can see the bonds, the double bonds, as being localized between two atoms in the molecule if you don't combine the atomic orbitals together. But over here in this section, we combine atomic orbitals to make one huge or one set of molecular orbitals. Therefore, electrons are not restricted anymore to the oxygen 1 and 2, like they show you right here. They're able to actually spread it around. Now, weirdly enough, this point, they show us Lewis's theory. This is literally Lewis's theory. This is valence bond, right? But then there's no molecular orbital theory. So for this part here, I'm going to detour real quick and Google molecular orbital of ozone. Hopefully I see that. When I search for the internet, I'm usually afraid of what I'm going to see. Okay. Okay. This is not bad. Okay. So here they're showing you ozone, right? The three oxygens, oxygen, oxygen, oxygen. They went through the anti-bonding. You see how they're not bonding. Then there's such a thing as non-bonding. And then you have the bonding. So I wanted to show you really just the bonding part, right? That in the molecular orbital theory version of ozone, the electrons are not localized between oxygen 1 and 2 or 2 and 3. They're spread evenly between all three oxygens, like the picture shows here, where we have 0 nodes. Okay, here, here. So hopefully you see that. Somehow in the PowerPoint they didn't put a picture. I'm like, how do you end on such a cliffhanger? Like, we're gonna have this chapter again. We don't. This is the end of this chapter, right? So imagine this picture was added to that slide. Then that would be the valence bond model, where you have the oxygens, the 3 oxygen here, here, here. Then you have a big blanket looking thing on the top and a big blanket looking thing on the bottom. Sandwich looking thing. Looks like a little monster. Anyway, this is molecular orbitals here. They should have drawn the picture because my picture is horrible. Okay. But yeah, that's it. And that's the end of the chapter. Any questions? But yeah, so when we're drawing the orbital diagrams and stuff, we really need to go back to that electronic configuration table, which I think I put this in the previous section, to really use this table to help us remind us what element are we dealing with, what group is it in. If it's one of those S elements, then we're going to be dealing with circular orbitals, right? P elements figure 8 and vice versa. Anyway, this is all I have for today. If you have any questions, so I'm hoping that by next time, yeah, I don't know what happened here. I was really trying to get, yeah, this is what I'm talking about. The apps are not working, and this is where my my PowerPoint uploads to, so I was not able to access it. So hopefully it gets fixed by Wednesday. But anyway, if you do have questions in your homework, please let me know. You can just send me email. I can answer it. Other than that, I am done.